Here are a couple other ways you can use the sum formulas to figure out new identities. So let's start by simplifying x plus pi. So this is a function of x, but still it has a sum inside of our trig function, so we can use the sum identity for sine to see how else we could write this. So the sum identity for sine says sine of the first angle, so sine of x, times cosine of the second angle, so that's cosine pi, plus cosine of the first angle times sine of the second angle, that's pi. Okay, so this is sine of x times cosine of pi, that's minus 1, plus cosine of x times, well, sine of pi is 0. So this whole thing is just minus sine of x. If you look at a graph, that actually should be apparent, because sine of x looks like this. Sine of x plus pi, well, this middle spot here is pi. And so if you take this graph and shift it to the left pi, then you get this graph, which is just the negative of sine of x. So that's something that we probably suspected before, but now we've proved it using the sum formula for sine. All right, let's have a look at another example. So let's find a nice expression for cosine of inverse sine of u plus inverse tangent of v. And when I say a nice expression, we'll have to decide as we go what that means, just by simplifying our result as much as we possibly can. Well, to start out with, we have a sum inside of our trig function, so let's use the sum formula for cosine. We get cosine of inverse sine of u, so cosine of the first one, times cosine of the second one, so cosine of inverse tangent of v, minus sine of the first one, so sine of inverse sine of u, times sine of the second one, so sine of inverse tangent of v. Okay. And we could think about stopping here, but if you remember, when we had trig functions, inverse trig functions inside of trig functions, there was some simplifying we could do to make it nicer. So let's do that. Let's do that work. To do that, we drew a most important diagram of each of these situations. So let's start with this one. Okay. So we're going to need a circle, and we need to draw an angle in here so that sine of this angle is u. So I can make the hypotenuse 1 and the opposite side u. And so sine of this angle is u because it's opposite over hypotenuse. And then find the third side using the Pythagorean theorem. It's the square root of 1 minus u squared. And now we're ready, so we might call this angle theta. Now we're ready to evaluate any trig function that has theta in it. And there are actually two. There's this cosine, and then there's a sine way over here. We're going to need to do the same thing for v, so let's draw a version of the most important diagram with v in it. Circle isn't quite as good this time, so we need some angle here. We could call it maybe phi, so let's call this angle phi. And that's inverse tangent of v, so we need to label the sides in this little right triangle so that the tangent of the angle is v. Tangent is opposite over adjacent, so if we put a v here and a 1 there, then tangent of phi really is v. And that makes the hypotenuse side here the square root of 1 plus v squared. All right, now we're ready to simplify all of these trig expressions. So cosine of theta, we can use our diagram. That's adjacent over hypotenuse. So that's the square root of 1 minus u squared. times cosine of inverse tangent of v, so that's cosine of phi. So we can use this diagram to write down cosine, and that's 1 over square root 1 plus v squared minus sine of inverse sine of u, that's u, and then sine of phi, again, we can use the diagram, that's v over the square root of 1 plus v squared. All right, now both of these have the same denominator, so we can put them over a common denominator, square root of 1 plus v squared, and then this left-hand part, square root of 1 minus u squared minus u times v. And that's about as good as it's going to get.